So now let's take a look at random variables and define formally what we mean by this. The intention is to describe the potential outcome of an experiment. So in other words, we're going to do an experiment tomorrow, and the outcome might be any sort of real number, and we want to associate probabilities with this before we actually get the numbers. And the way this is normally done is to say that we start with a function from the possible outcomes out to the real numbers. And what we need to do is, we want to be able to talk about probabilities of certain things happening. And that's just going to be the probability of the outcomes corresponding to certain events in the original space. So if you like, this is the probability of the sets of omegas such that x of omega is in this outcome B, which is on the real line. So that's the fundament of a random variable, and we can now already do certain things with this. We can, for example, define what we mean by a cumulative distribution function, sometimes called a distribution function in probability theory, but always a cumulative distribution function in statistics. And if we only have the probabilities, for example, in this form, then we can just define x to be the identity function on the real line, and that will give us the random variable with the probability distribution. Now, there are two important cases to consider. One is continuous random variables, and the other one is discrete. And basically, a random variable is discrete if the probability of a positive number of an outcome is positive, if the probability of outcomes is positive only for a countable number of x values. And in that case, we can talk about a probability mass function. And of course, you notice, because these have to be probabilities, that the mass function has to be non-negative everywhere for every real number. And the sum of p of x across all real numbers is equal to 1. The other common type of random variable is the continuous random variable, and that's simply a random variable which is such that the probability of x being in a set on the real line is the integral over that set of some function. Now, for this to work, of course, the function f has to be such that f of x is greater than or equal to 0 for x, every real x, and the integral over the entire real line of f of x dx has to be 1. Otherwise, it's not a probability. So those are the two most common types. It's possible to do different things. It's possible to combine the two into one definition, but this is enough for us at this stage. And there are plenty of examples. For example, if you do two causes of an unbiased coin, this is the sample space, and this could be, it's actually using Icelandic notation, but this would be heads and tails in combination of heads and tails in English. But now, if x is the random variable to indicate the number of heads that you receive, then if you have two tails, then of course that's 0. If you got heads, tails, or tails, heads, or heads, tails, get 1, and so on. So, and we can now talk about the probability that x is 1. This has meaning now, since it's just the probability in the original case of getting a 1, and that is the probability of one of these two. So this is the probability of x inverse of the set containing 1 in ordinary set notation. And this then is the inverse set of 1 is just the probability within the omega space of the set Ks or Sk in this case. And that probability will depend on whether it's a fair coin or not. So this should give you the background of the definition of a random variable from a purely mathematical viewpoint. And that's enough for this particular short video.